Hello everyone, my name is Johansson and my register number is URK25CS1018. This is my practicum number 3 and the topic of this practicum is campus navigation using breadth first search or BFS. In this program, I have represented different location of the college campus as a graph and I used the BFS algorithm to find a path between the two locations. So first I import deck from the collections module. So deck basically means double-ended queue and I use it here to implement the queue required for breadth first search. So I have created the dictionary called campus underscore map. This represents the campus as a graph. Each key represents a location and the corresponding list contains the location directly connected to it. For example, in here A is connected to B and C, and in the fifth line you can see B is connected to A, D and E node. So I have also created another dictionary called location underscore names. This is used for mapping each like a letter to an actual campus location. So for example, A represents administration and B maps to library, C maps to cafeteria and so on. So now coming to the main part of the program, I have defined a function called BFS. So basically this function takes four parameters: the graph, the starting location and the goal location. So actually inside the function I created a empty list called visitor underscore order to store the order in which locations are visited. Then I create a set called visitor and initially added the starting node to it, as you can see. After that I created a queue using deck. The queue initially contains a path consisting only of the starting node because we want to initialize starting node. So the while queue loop continues as long as there are paths available to explore. So as you know, BFS explores all possible paths. So in this loop, we are using while queue to loop continuously as long as there is path available to explore. Inside the loop, you can see there is pop left or function which removes the first path from the queue. So the next is then take the last node of the path using path of -1. This takes the last node of the path. This represents the current location being explored. I add this node to the visited order. Then I click then I check whether the current node is equal to the goal. If it is equal to the goal node, the function immediately returns the order in which the location were visited and the path that was found. So if the goal has not been reached, the program checks all the neighboring locations, and for every location that has not been visited, I added to the visited set and add a new path to the queue. So this is how this function works. The expression a path plus neighbor creates a new path by adding the neighboring location to the current path. This is how BFS explores the graph level by level, as you can see. And next I have created another function called run search. So basically this function is responsible for running the search and displaying the results in a readable format. It prints the algorithm name for the formatting, the starting location and the destination. Then it calls the BFS function and receives two values: the order of visited locations and the final path. Okay, as you can see, the program then converts the location letters into the actual names such as administration, library, parking and research lab, as we did create a library here. So if a path is found, the program displays the complete path, also calculates the number of hops using len of path -1. This is the formula for calculating the number of hops. So and finally inside the if statement, I specify the starting location as A, which is administration of course, and the goal location as J, which is the research lab. Then I call the run of search function with BFS. In this example, the program starts from administration and searches for a path to the research lab. The important concept demonstrated by this program is birth first set. The BFS explores all nodes at the current level before moving to the next level. This is the basic definition we can give it to the BFS. Because of this, when all edges have equal costs, BFS can find the path with the minimum number of hopes. But the criteria is every edge has to have equal costs. Therefore, the program demonstrates how BFS can be applied to a real world situation, such as finding a route between locations in college campus. Thank you.